Okay, so we're continuing on looking for patterns and talking about the slope. So in example 2, identify a pattern, in other words, a relationship between x and y for each table below. In these examples, we will simply look at the pattern between x and y as we continue to study linear equations in two variables. We will develop a formal method for identifying linear relationships between x and y. So what do you notice, what could you say is happening in this column here for x? What would you say the pattern is? Yeah, so over here we're increasing by 1. And what's happening over here? Decreasing by 4 every single time. Every single time we increase by x is 1, we decrease by 4. So that could be like if you spend $4 out of your account. Oh, it's increasing by 4? Oh, I thought she said decreasing. Sorry. I didn't look closely enough. Okay, it's increasing. This is increasing by 4. So later on when we get to the slope formula, what we're going to realize is our change in y over our change in x is our slope. This is our rise and this is our run. This is the definition of slope. So since we increased here by 4 for every 1, oops, 1, that's a 1. What is that number, 4 over 1? 4. That wasn't a trick question. You're like, is that too easy? It's just like you walk around all day and you are over 1, but we don't see it. It's implied, right? Until the sun comes out and then you see the 1 denominator on the ground, your invisible 1. Okay, let's look at table 3 here. What's happening here? You see a pattern? What pattern do you notice with the x values? Yeah, and that's actually very typical. In all of these, not all of these tables, this one's not that way, but when we set up a table, we talked about the x value as being the independent variable. And so usually we are going to use a table where we are going to increase by 1 and we will start around the origin. But that's totally our choice. Whenever we create a table of values, we have that choice since x is independent to decide what values of x we want to use. When we were talking about fractions before, when I said if you're going to make a table of values and your coefficient of x is 1/2, what numbers did we like to count by in our table when we had a fraction? Yes, even or multiples of 2. Because then we didn't get any fraction as the answer. If we had a denominator of 3, what numbers did we use as x? Yep. If we had a denominator of 4, what numbers did we use for x? If we have a denominator of 5, what did we use for x? Yes, multiples of 5. So multiples of the denominator make it so that you don't have to graph a fraction. But here, these are also increasing by 1. And what are the y values doing? Increasing by 4. So actually, this has the exact same slope. But look at how the numbers are different. So this slope is going to be equal to 4 over 1, which is 4. What is the main difference that you notice in the table? Is there anything different? What's that? Oh, you think they would be parallel, and that we're going to get to that later, Sierra. That's exactly right. When they have the same slope, they will be parallel. Notice that they have different starting places, and I say starting places even though you're like, well, that's not exactly where it starts because we had negative numbers. But I'm saying starting numbers because I'm talking about this specific point. Do you remember what that point is called from the other day, our discussions? We were saying, why is 0 so cool? What does x equals 0 have to do with anything? It has a special name. It's going to happen on the y-axis. It's called the y-intercept, right? So here, when we get to identifying the equation, this one is just going to be y equals 4x. This one is going to be y equals 4x plus 1. And again, we're going to get to all that. I'm just kind of throwing it out there right now so you can kind of start to see it's not that hard to figure out. Later on, we'll see. That'll work, by the way, because if I go 4 times 1 plus 1, I get 5. 4 times 2 plus 1, I get 9. And that's because of that y-intercept right here. Okay, let's look at this table. So here we have how is our x values increasing and how are our y values increasing? Yep, so here's our change in x equals 100. By the way, that little triangle means delta, which means change. So it doesn't mean triangle in this sense. It just means change in x. The x values are increasing by 100. What are the y values doing? Change in y is 10. So if we go change in y divided by change in x, that's going to be 10 over 100. So the slope will be 1/10, right? And essentially, if I take 1/10, that my equation is going to be y equals 1/10 times x plus 0, because this is my y-intercept. And if you notice, if I take a tenth of 10, or a tenth of 100, I get 10. A tenth of 200, I get 20, right? I'm dividing each number by 10. That's the pattern going this way. Okay, how do our x values increase here? By 1. Change in x equals 1. What's our change in y here? Is it constant? It's different every time, right? Here, I would subtract 3. Here, I'd subtract 1. Here, I would add 1. Now I'm adding 3. Now I'm adding 5. So when you don't see that you're increasing by the same number in your x and also a consistent increase or decrease in y, we're going to call this one is actually nonlinear. Does anybody know what pattern that is? This is kind of a famous pattern. Do you see any other relationships between the numbers? Yes? X squared. She has the equation. This is you're ready for Math 65, I can tell already. Y equals x squared. We call this one, this is what we're going to deal with in Math 65. This equation is quadratic. How did you come up with that formula right here? Negative 2 times itself is 4. 2 times itself. Yes, 3 times itself. So she squared the numbers, so she just noticed that pattern. And that's a really cool pattern to notice. It's really good also to, in addition to knowing our times tables by heart, knowing the perfect squares. Do you know what I'm talking about, perfect squares? Is also really helpful. That's what we were talking about before with like 13 squared is 169. So if the table had continued to 13, we'd have 169, 14, 196. I like that because those are like opposites, or like, you know, it's a transposition error. 15 squared, does anyone know that one? I just like to show off. 16 squared, 256. You've probably seen 256 a lot of places before because that gets back to the powers of 2. Anyway. All right. Any other questions about this? Are you kind of getting this idea? If the change in x is consistent with a similar change in y, meaning we could skip numbers. We don't necessarily have to go in order, but I have to have a consistent rate of change. Okay, so let's return to this idea of the chickens. Assume the initial cost of purchasing a flock of chickens and all the equipment is $400. Also assume that each month they cost $20. Let y be the cumulative cost of owning the chickens in dollars, and let x be the number of months they are owned. So what did they do right here? Let y be this, and let x be that. What do we call that again? Yes, defining the variable. Because if you didn't have that part and you had to write an equation, you would have to first define the variable. Define the variable So here, does this equation make sense? Y equals 20x plus 400. Where's the 400 coming from and where's the 20 coming from, and why is the 20 next to the x and not the 400? Starting point, I like that. 400 is the starting point. The initial cost, yes? Yeah. And x is the number of months. So it makes sense that we're going to multiply 20 by x. Once we add this together, we'll have the total cost. How does the cumulative cost change over the first 5 months? So if we were to calculate, okay, month 0, 20 times 0 plus 400, y equals 400. And she said this is the initial cost. Now, first 5 months, y equals 20 times 5 plus 400. How much is your total cost after you've owned the chickens for 5 months? 500. So how much did your y value change? And how much did your x value change? So you went from 400 to 500. That's a change of how much? 100. Because 500 minus 400 gives us 100. You went from 0 months to 5 months. How much did your x values change? 5. What's 100 divided by 5? 20. Your change is $20 every month, right? And this is our slope. Later on, we're going to learn that we're going to use M. M is it actually comes from the French to measure, mesuretur or something. Who speaks French? No? A little bit? Which is an abbreviation we use for slope. How does the cumulative cost change for the first 10 months? How does the cumulative cost change over a period of 1 month? What do you think the cumulative cost is going to change over 10 months if we see this pattern continuing? It's going to be 600, and so it will have changed by 200 for 10 months. How much does that divide down to? $20 per month. Still, it's the same thing, right? How does the cumulative cost change over a period of 1 month? Every month it changes by $20 per month. So when we look at the graph here, and let's notice some things about the graph. What is the scale that is being used on the y-axis? 100. They're counting, each line counts for 100. What's the scale that's being used on the x-axis? 1. What about this point? What do we call that point? Y-intercept. The y-intercept is like what Sierra was talking about, is our starting point, 0, 400. How much are we changing every month? Going up 20 over 1, $20 every month. That's why you see it goes up $100 over 5 months, because $100 over 5 is the same thing as 20 over 1, right? It went up $200 for 10 months because 200 over 10 is the same thing. These are all equivalent fractions, aren't they? And what you're seeing here is this is our rise in cost over our run, which is months. So our rise of $100 over 5 months, $200 over 10 months. So we could say we're going up $100 for every 5 months, which is the equivalent of $20 per month. Okay, it's kind of, hopefully that makes sense. Seems a little, does it seem obvious? Kind of, but it's still kind of important too to realize. And then here we have, you notice also some things about the graph. We have the label of the axes and what it represents, and here we have the label y and what y represents. Again, that's like defining the variable. Okay, any questions on that? Okay, let's go on to the next thing. Talking about the slope. The slope of the line is the ratio. What does ratio mean? Makes you think of what? Fraction. A ratio, the definition of ratio is a comparison of two numbers using division. So if I compare something to something else, I'm dividing. That's a fraction. Essentially, that's a fraction. So it's a comparison of the vertical change to the horizontal change. Vertical change is your change in y, and horizontal change is your change in x. And this is literally the slope. Given the 2 points, and we say x1, y1 because that's just saying that's the first point. We say x2, y2 because that's just the second point. So it actually doesn't even matter which point is the first one and which point is the second one, so long as you're consistent. So we have this formula, and again, we're using m to signify the slope, and that comes from the equation y equals mx plus b, where m is the slope. And what did we say b the other day? We were talking about b. What was b? The y-intercept, remember? Because if you plug in 0 for x, the only thing that's left is b. And that's one of the easiest points to find. And you also pointed out that it's usually the starting point. So on this graph here, right here, identify the slope of each line graphed. What we're going to want to do is identify what the points are. So let's put some ordered pairs on these. What's the ordered pair for that y-intercept? This one right here. 0, -1, and this one is 1, 3. Okay, yes, because I said y-intercept, that's why I wanted to get that one that's on the y-axis. Okay, so if we were going to come up with the slope, we could call this our first point and this our second point. So what I do is I literally take my pen and I write, okay, here's x1, here's y1, here's x2, here's y2. Now I'm going to use this formula. The slope is y2 minus y1, and by the way, there are implied parentheses there because you do have to do that subtraction first before you divide, and then there's implied parentheses x2 minus x1. So if I plug that in, I'm going to get y2 is 3, y1 is -1 minus -1 over x2 is 1, x1 is 0, 3 minus -1. What's that? Isn't that plus a positive, right? So 4, oops, I meant to put a 0 here. 1 minus 0 is 1. Now if we look at the graph, I'm going to rise 1, 2, 3, 4. That's my rise. And 1 is my run. Slope is just rise over run. So either the formula, usually you use the formula when you just have points, but if you have a graph, it's easy. You can just count the rise over the run. Okay? So later on we'll learn that the equation here is going to be y equals, based on this equation here, 4x minus 1. Do you see where I'm getting the -1 from? Yeah? What would be the slope on figure 5, even if we don't have the points? I mean, if I don't even identify the points, can you tell just looking at the graph what the rise and what the run is? What is it? What would you say it is? 1 over 1. Rise 1, run 1. To get from point A to point B, I'm going to go up 1 over 1. So my rise over my run is 1 over 1, which is equal to 1. What's my y-intercept here? 0. B is equal to 0. Can anyone tell me, based on this equation, y equals mx plus b, what the equation of this line would be? Y equals x, because there's a 1 plus 0, right? If you have this is the same thing. Y equals x has an implied 1 as the coefficient and plus 0 as the y-intercept. You don't really need the plus 0. I'm just showing you that it's there. Because a lot of times people will say, they'll look at an equation like this and they'll say, even though that's like one of the most simple equations you could look at, right, is y equals x, a lot of times that is the most confusing one for people. And they'll say, there is no y-intercept because they don't see the 0 there. You just have to imagine it's there, the plus 0. Okay, so let's have you guys try calculating the slope on these two problems. They're a little bit harder, but I showed you how you can use this formula. And I would literally start by going x1, y1, x2, y2. That way, when you write the formula down, you're just plugging those numbers in.